Good morning, everybody. Today I'll be presenting an overview of quantum cryptography with a particular focus on quantum key distribution. Based on the work of David Ruska and Nicholas Gisin, our objective is to trace how secure communication standards have evolved from classical cryptography to quantum secure key exchange, and to highlight how quantum key distribution addresses the emerging risks posed by quantum computers. Let us begin with the historical background that led us to the need for quantum secure communication. So, cryptography has always evolved in response to communication technologies. Earlier ciphers, such as substitution codes, were sufficient for ancient civilizations, and then mechanical era came. We saw more sophisticated systems like Enigma systems, whose decryption dramatically influenced World War II. With the arrival of telecommunications, the internet, online banking, digital commerce, etc., cryptography became a key essential for everybody, not just governments. Today, secure communication protects national infrastructure, financial systems, and even routine personal exchanges. This growing dependency on digital systems is precisely why the future demands security that is not just computational but also unconditional, a requirement that lays foundation for quantum communication. Modern public key cryptography, especially RSA, ECC, etc., they rely on mathematical problems which are considered hard for classical computations. However, as we can see that Shor's algorithm fundamentally challenges this landscape. It offers us efficient way to factor large integers and compute discrete logarithms, which are the core assumptions of RSA. Although we do not have a large-scale quantum computer yet, uh, the risks which are associated with this kind of a system and the community also agrees that advancements are inevitable. This creates a critical vulnerability. Encrypted data today can be stored and potentially decrypted in the future, a scenario often referred to as harvest now, decrypt later. So quantum resistant solutions are an immediate necessity. The response to this emerging threat has taken two directions. First is post quantum cryptography, which introduces new algorithms, new mathematical constructors, which are believed to be even secure against quantum algorithms. These computation solutions still rely on hardness assumptions. Secondly, quantum cryptography takes a fundamentally different approach. It leverages physical laws of quantum mechanics, such as uncertainty principle, the no cloning theorem, to guarantee that eavesdropping attempts are completely detectable and can cause disturbances. Quantum key distribution is the clearest example of physics-based model. It enables information theoretical security regardless of adversaries' computational powers. So what did we land on? We landed on BB84. This is the foundational quantum key distribution protocol. So it was introduced by Bennett and Brassard in 1984. It's the cornerstone of quantum key distribution. So it goes as follows. Alice randomly prepares single photons in one of two bases, rectilinear or diagonal. And Bob measures each incoming photon using a random basis. After the transmission, they publicly compare the basis choices, not the measured bits, the choices, and matching rounds form the key. The security arises naturally from quantum physics. If an eavesdropper attempts to intercept and measure the photons, that person inevitably introduces errors because that person does not know the basis. Further, the no cloning theorem ensures that qubits cannot be copied perfectly, like preventing time-based delayed measurement attacks. So the B84 provides a simple yet profound illustration of how physical laws can enforce cryptographic security. So although BB4084 has secure in theory, practical implementations introduce some imperfections. Real photons often emit weak signals, such as electromagnetic signals or something like that, rather than true single photons. This and like results in multi-photon emissions occasionally. So this opens new doors, the photon number splitting attack. An adversary may remove a photon from each pulse, store it, and allow others to pass undisturbed. After basis reconciliation, that stored photon can be measured in the correct basis, and the person can find out the key without disturbing the channel. Additionally, side channel vulnerabilities such as Trojan horse attacks or detector binding, all of these target hardware weaknesses rather than protocol itself. These real world considerations motivated refinements to strengthen quantum key distribution. So, the modern quantum key distribution, the decoy state method. The decoy state method is the most influential practical advancement in QKD. Instead of sending all pulses with the same intensity, a randomly interspersed low density decoy pulses amongst the regular signal pulses. By comparing the detection statistics of these different intensities, Alice and Bob can accurately estimate how many detections correspond to genuine single photon events. If an eavesdropper attempts a PNS attack, as we talked earlier, the discrepancy between the signal and the decoy statistics expose the presence. The innovation, this innovation restores secure long distance operation readily using laser sources, making decoy state BB84 the backbone of modern deployments. While quantum key distribution uses single photon, discrete variable quantum key distribution uses single photons, continuous variable adopts a different approach. So what it does is it encodes information in the amplitude, phases, uh, quadratures of a bright laser pulse. This is familiar in technical telecom systems, and this gives us quite a few advantages. We like compatibility with current standard telecom hardware, high secret key rates over metropolitan distances, and efficient hybridyne or heterodyne direction. However, security analysis is more mathematically involved due to the infinite dimensional Hilbert space. Furthermore, losses translate to noise demanding sophisticated strategies to for error correction, etc. Despite this, continuously variable quantum key distribution still remains an active, promising direction. To address vulnerabilities in detectors, measurement device dependent QKD was introduced. So in this, both Alice and Bob send the states to an untrusted central node that performs a Bell state measurement. Since detectors are no longer part of the trusted boundary, detector attacks become ineffective. A more recent breakthrough is the twin field quantum key distribution, which replaces two photon interference with single photon interference. This changes the scaling of key rate with distance, allowing secure key exchange over distances once considered unreachable, now even exceeding tens and thousands of kilometers of optical fiber. These developments in quantum key distribution push push it closer to global long distance quantum networks. So to conclude, quantum key distribution represents a decisive shift in in computational assumptions from security to physical law. From foundational BB84 model through various practical improvements such as decoy sheet method, sophisticated means like MD, quantum key distribution or twin field, the field has matured rapidly. Today, quantum key systems are moving from research labs to commercial deployment, offering a credible pathway towards future proof communication in a post quantum world. This concludes my presentation. Thank you.